and doesn't belong to the closure of gamma, we want to know the rate at which the law through the perturbed system of gamma goes to 0. So if you are interested in the exponential behavior, you are in the field of large deviations. Okay, so I recall what a large deviation principle is. If you take a family of probability measures that are in Polish space E, then you say that this family satisfies large deviation principle of a certain speed, 1 over epsilon, and with respect to a certain action functional, that is defined on E and taking value in 0 plus infinity. If the level sets are compact in E, and if these two conditions has to be fulfilled simultaneously. So for each A, you have this bound from, sorry, I always, below and above, I never know what is below and never know what is above. One is above and the other is below. So, in the case of the linear random perturbation, it is very well known that you have a large deviation principle under certain hypotheses on the coefficients. With respect for the law of the solution of the perturbed system from the trajectory of the unperturbed one, and the action function is given by the following infimum, where phi is the control that substitutes now the random perturbation, and you take the infimum over all the control such that you can replicate your f through the solution of the following equation. Okay, so why linear? It is linear because if you associate to the SPDEs the nonlinear Kolmogorov equation, and now takes value in h, so x belongs to h, so it is a Kolmogorov equation in infinite dimensions, then if you see, you have all the coefficients that are linear, in particular, there's the second order term depends only on x. Okay, and you, under suitable condition, you can associate to the solution of, you can find a classical solution for this linear Kolmogorov equation, and they can be written in terms of a transition semigroup that will depend on epsilon, since we have a family that corresponds to the family of perturbed SPDs. And this semigroup turns a transition semigroup is a linear transition semigroup because everything is linear here. So the large deviation principle works and also allows to describe long time behavior for the solution of the Kolmogorov equation, so for the U epsilon. In particular, using the action functional and some other things, you can characterize the following behavior as epsilon goes to 0 of the solution of the Kolmogorov equation. Outside then a limit time interval, you can study the behavior for a large time that goes to plus infinity in a specific way. And this lambda depends on the peculiarity property of the action function. So, in 2010, Friedlin and Krylov extended the theory of large deviation principle to the case of quasi-linear parabolic problems in RD. So I mean that there is now a nonlinearity, and the terms of the second order depends on the solution itself. And by AEG, I, as usual, consider the following sigma sigma star, where sigma is the coefficient that was in front of the Martigal term in the perturbed system number 2. So, since you are in finite dimensional, the theory of a quasi-linear equation is well established, and there are several set of conditions that allow to get a solution, and a regular solution, so a classical solution for this kind of problem. And if you fix T now, you can associate to the equation before this this stochastic differential equation. I am in finite dimensional here, where U is the solution of the Kolmogorov equation. You need to fix T, and you have to go backwards for the solution of the PDE. And so for each T, you have a family of perturbed system. And what you can get is still that you can write down your the solution of the Kolmogorov equation through a semigroup T epsilon T that now is a nonlinear semigroup. And so that's why I was at the beginning. The title of the talk is about Quasi-Linear Kolmogorov equation, and it is about nonlinear random perturbation. The nonlinearity is related to the fact that now the transition semigroup is any more linear. Okay, so together with Sandra Cerrai and Gianmario Tessitore, we wanted to do the same thing in infinite dimensions. So the same, we wanted to prove a large deviation principle for the equation in the case of nonlinear, in the linear case, and then we wanted to continue the study of long-time behavior for the solution of the Kolmogorov equations. Using the functional and some other things that were introduced by Friedin and Korolov. So the first things to consider is the infinite dimensional Kolmogorov equation that is corresponding to the nonlinear one. So here I have, so we start from here. This is a Kolmogorov equation where the second order term depends on the solution itself, okay, and X now lives in a Hilbert space. And unfortunately, there are not, in the current literature, results on well-posedness of such kind of equations. So the first thing that we had to do to start our program was to find a solution for well-posedness for this kind of equation. And so this is a really initial result. So we had to find a sigma that is a very particular shape. So I remember you, sigma is the term in front of the noise. And so it is exactly the term that you see here, okay? And we need to ask the sigma such that sigma star can be decomposed with a certain operator that is constant, and then a certain function that depends on x and r. So r will be substituted by u epsilon then, okay, with a certain delta that unfortunately I needed to put here in front of f. So this q can be must be a non-negative symmetric operator, but it doesn't have to be trace class. So while this f has to take value in the case of trace class and positive operator. So we have been inspired to use this kind of first perturbation of a Nonlinear case from the papers by Da Prato and Cannarsa of 1996, where they tried to study, they study actually the case of an elliptic perturbation of the Dorsten-Uhlenbeck case. Okay, so for the moment, we are able to handle only the case where delta is sufficiently small. Our idea, of course, would be to remove this condition, but for the moment, we are not able to do that. Okay, so just an example that fulfills my hypothesis. If you take as H the space of L2 function defined on a smooth bounded boundary, and you take an orthonormal basis that is contained in an infinity of O, and then you introduce some lambda I, and if this condition is verified, then you can define your F on the direction of the orthonormal basis, introduces some Fi that are regular, smooth, times lambda I and the basis here. So this is a typical object that we can enter. So what we ask on the operator? We ask the operator to be a generator of a C0 semigroup of negative type, and then we ask the typical requirement on PT, so to be class, and then we ask the same controllability condition that Federica was mentioning before lunch, and so that this operator is well defined, and also we need some regularization property because we say for classical solutions. Moreover, we ask on sigma not only the particular shape on sigma star, but also that this regularity if you apply the semigroup, you need this regularity to give meaning to the stochastic integral. And also, you have this kind of blow up here in the growth and also in the Lipschitz condition that allows you to integrate easily. Okay. So all these assumptions are verified. For instance, if you take A, the realization of the Laplace operator in the interval, so 1D, and you take Q, the identity, so you can cope with white noise, but only with dimension 1. So you rewrite your, is the same thing. I just rewritten my Kolmogorov equation. As I said, the trick is to consider it, this Kolmogorov equation, it is quasi-linear, as perturbation of the Orsten-Uhlenbeck operator. So L epsilon is the Orsten-Uhlenbeck operator, and then you still have a term that is of order 2 with an epsilon in front, and then you have this other term of order 1. This one is not a problem. Of course, the problem is this one because it has the same degree of the Orsten-Uhlenbeck operator. And so our strategy, as I said, inspired by the Canarsa, is to treat these two terms as a perturbation of the Orsten-Uhlenbeck operator. So what we could prove is that if you take an initial datum that is older, continuous, with a certain Eulerianity, a big order exponent, and then you need to fix a theta that is they stay a little far from eta, and then you introduce a rho that is the following quantity that stays between 0 and 1 fourth. Then you can find delta bar such that for each delta less or equal to delta bar, each epsilon, and each t, there exists a unique classical solution. Moreover, this classical solution has the following regularity. So you get the same regularity of the initial datum for the solution, and then you have an integrable blow-up for the first derivative, and you have an integrable blow-up in the space C theta, also for the second derivative. Okay. And this constant here, and this is really important, doesn't depend on t. Now, I'm supposed to finish. So, first of all, you write down some few things about the steps of the proof. First step, you write down your solution in a mild form, and then, since our hypothesis, you can prove that the transition semigroup RT is it is the Orsten-Uhlenbeck semigroup has the following regularity properties. And so, having these properties, you can construct a suitable space of smooth order continuous function with this blowing that I showed you before in the previous slide. And then you can use a fixed point argument to prove that if delta is sufficiently small, then you get a local solution in the space of function that is given by the order function such that this norm is finite. Step 2, then you have to show that any mild solution actually is a classical solution. And by classical solution, I mean the usual definition. So you can evaluate two derivatives of your solution. Moreover, this term that is in front of the second order term is S1, which is class, and in time you have the following regularity, and it solves, of course, the Kolmogorov equation. So then you pass to step 3, where you have to prove that your local solution is global and it is unique. And to get, as a first step, you must prove a maximum principle, and to do that you use the relation with the SDE associated, and so the representation of UT through the nonlinear transition semigroup. And then you have to prove some a priori bounds for the mild solution. Once you have these a priori bounds, then you can conclude that for every epsilon, your solution with that regularity is indeed unique in the space of classical solution with that regularity. So I come back to the stochastic PDE. As you see, this is a stochastic PDE that I wrote you before when I wanted to define the transition semigroup. Okay. And so, of course, as a byproduct of our result, we have that since U is very regular, so in particular it with a certain blows up in time, but this doesn't give a lot of problem, then you have that this equation for every t and every x as a unique mild solution in this space. So, of course, then you get the representation of the solution of the Kolmogorov equation for each epsilon through the usual formula, and as a consequence of the Markov property, you get that if you evaluate U epsilon in t minus s, that it is exactly the term that you find in the SDE, then you can see this quantity as the conditional expectation of the final datum evaluated at the terminal time t. And so you can rewrite your equation, your SDE. You can, in some sense, avoid this dependence through U epsilon, and the price to pay is to introduce here a conditional expectation. Why I did that? Because there is a mistake. I'm sorry, this should be an epsilon. Because if I set y epsilon as the conditional expectation of the final datum evaluated in the SDE at time t, then this becomes a process, because here there is the s that depends on the conditional expectation. And then it is possible to prove that x epsilon and y epsilon together, they solve, at least heuristically, what's so-called forward-backward infinite-dimensional stochastic equation. So here you can recognize our SDE related to the Kolmogorov equation, because this term here is exactly the conditional expectation of the final datum. And then there is the backward part where y epsilon is represented through the Martingale representation theorem, solves the following equation. And you fix the final datum for y, you have an initial datum for x. So this is a two-point system, a differential system, and it is fully coupled in the sense that y appears in the forward equation, so the one that has the initial datum fixed, and so you have the typical. You cannot follow the typical approach of forward-backward system where you have you don't have these terms, so you solve first the forward equation, then you plug it in the final datum, and you solve the backward equation. These kind of systems have been studied since the 90s, and they were introduced by Pardue and Peng, and they provide, whenever Y is not present here, a representation of a probabilistic representation for the solution of a semi-linear equation. So as soon as sigma depends also on Y, then this gives you the representation of the solution of a quasi-linear equation. And so in finite dimensional, this system is well understood and well was proved with several techniques. But the most popular technique is unfortunately the four-step scheme that relies a lot on the solution of the Kolmogorov equation. So the scheme usually works like that. You start with you want to solve your forward-backward system, you write down the Kolmogorov equation that is quasi-linear, you use the results by Ladizenskaya and Haber to solve your solution, you get a classical solution in order to perform the Ito formula, and then you come back. And then you use the forward-backward system to get extra properties, for instance, that works also for they tells you something also new also on the PDE counterpart, but the typical way of solving this forward-backward system is the following one. And so, of course, actually, when Sandra Cerrai started to explain us her idea of doing Korolov work, she said, okay, let's write the forward-backward system, solves the forward-backward system, this gives us a representation for the solution of the Kolmogorov equation. But unfortunately, we were not able to solve it because the typical scheme relies on the existence of the solution already for the PDE context. So as I said, what I was saying, it is written here. So large part of the analytic techniques are not available. There are some, actually there is one paper, that is the paper by Pardue and Tang, where they make a lot of energy estimates, but they need to ask some quantitative condition on the coefficient that more or less are the same as our delta small. So these two slides are to say that you don't get a lot of knowledge from the forward-backward system in infinite dimension. And so and this is, it is different from the linear case, where the representation through the SDE gives you a lot of information for the linear case in infinite dimension, while here is the information that you can get on the stochastic counterpart. For the moment, this doesn't seem so powerful. So, of course, you can extend to infinite dimension this result more or less in the similar way of Pardue and Tang. So you can actually prove the well-posedness of the forward-backward system. And so once you have a y and x, you can you can define your solution of the PDE, the Kolmogorov equation, using the definition, the very definition. The problem is that you have no regularity, and so you don't even know exactly the formulation, in which formulation you are solving your PDEs. So you don't have regularity for the PDEs. Okay, so with our approach, we could prove the LPDE principle, the large deviation principle. And it turns out that the large deviation principle for our system still is true also in this nonlinear case. The action function is the following one, where you see this is the control, these phi are the control, they substitute the Wiener process here in the random perturbation. You don't have epsilon anymore. So this is exactly the nonlinear counterpart of the equation that I have introduced at the beginning for the replication of f. And this is just what you think to be the limit as epsilon. If you take epsilon equal to 0 in the Kolmogorov equation, you end up with a first order equation, and this is the ODE in infinite dimension related to the limit equation. Okay, and technically, we proved the L large deviation principle using the approach by Dupois of the weak convergence approach, the so-called weak convergence approach that was introduced by Dupois in 2008. And so, instead of proving large deviation principle directly, we show that our equations fulfills C1 and C2, where C1 is the compactness of the level cells as before, but C2 is the following weak convergence requirement. So if the controls are converged in distribution in the space of L2 with respect to the weak topology, you have to prove that the associated controlled equation behave properly. So as epsilon goes to 0, you have this convergence in distribution in the space of C0T with value in H. And of course, to prove this fact, we had to use our approach because we need some regularity of U epsilon that enters in the equation for the controlled perturbed SDV. Okay, so some references. This is the paper by Dupois where the weak convergence approach for LDP, for large deviation principle, was introduced. This is the paper by Frieden and Koralov, where the nonlinear perturbation in a finite dimensional case is treated. This is the classical reference for random perturbation in the book by Frieden and Wenzel. I cite also this paper because we used a lot all the estimates that are made in this paper by Alexander Lunardi and Michael Ruckner, where they study Schauder estimates for Kolmogorov equation in infinite dimensions. And then on the counterpart of our vector system, there is this reference book. This book that is a reference for the finite dimensional case. In infinite dimension, there's nothing, almost nothing. And here it is well explained the first step scheme, as I said, but there are also other way of solving this forward backward system in the case of coupled, in the digital case where the equations are coupled. And this paper by Pardo and Tang is the one that I was mentioning that I think, I never checked the calculation, but I'm pretty sure that can be extended in infinite dimensions to get a solution not very regular of the forward backward system. So thank you for your attention.